microscopy. So this is the updated version of the previous videos which I posted. So many of the students were unable to understand microscopy, so I made a repeat video. Okay, shall we start? So here we'll talk about the history, introduction, principles, uses, types and precautions. So in 1590, Hansen Zacchaeus Janssen created the first microscope. In 1665, Robert Hooke coined the term micrographia. In 1675, Antony von Leeuwenhoek, who used a microscope with one lens to observe the insects and other species. So this is the curly hair guy, Antony von Leeuwenhoek, and this is the microscope which he discovered. So why do we need to study a microscope? A good microbiologist must be a good microscopist. So I think this should be shown to my dearest madam. A good microscopist should understand the optical principles, the construction, function and maintenance of the microscope. Introduction. A microscope is an instrument used to see objects that are too small for a naked eye. The science of investigation small objects using such an instrument is called microscope. Parts. The supportive system. The foot, limb, the revolving nose piece, the stage and the mechanical stage. Magnifying system is the objective, eyepiece and the condenser which is containing the mechanical. So these are the parts of the microscope. So the tubular structure is the ball tube, the eyepiece, the arm, stage, coarse focus, fine focus, base, light source, diaphragm, stage clips, the objective and the revolving nose piece. I request every student who is seeing the microscope for the first time to pause the video for 30 seconds, look at it, memorize the parts and move ahead. So how to use a microscope? So always carry it with two hands. Only the lens paper should be used for cleaning. Do not force the knobs. Always store. So the general principles of microscopy: the magnification, resolution, contact and wavelength of radiation. Magnification. Microscope has three magnification: high, low and oil magnification. In addition to this, the ocular lens has a magnification. The total magnification is the multiple product of the ocular and the objective. So low power is 10x, high power is 40x, oil emission is 100x, focal length is 1/2. You can see that for 10x it is 16, for high power 40x it is 4, which is 1/4 of 16, and its oil emulsion is 2 mm. Okay. Contrast. Differences in intensity between two objects or between the objects and background is analyzed. Importance in determining resolution. Staining increases contrast. Use of light is the face increases contrast. Resolution power. It is the ability to reveal closely adjacent structures detailed as separate distinct objects. Unaided eye has a resolution power of 200 micrometers. Light microscope has around 0.2 to 0.3 micrometers. Electron microscope has 0.1 nanometers or less. Micrometry. Measurement of minute objects under the microscope using a micrometer is called micrometry. Two micrometers are there. First one is ocular and second one is stage micrometer. Stage micrometer consists of glass slide which is around 1 mm scale and divided into large division. One large division is graduated into 10 small divisions. So one small division will be 1/100th of a millimeter, that is 10 micrometers. So one small division is 10 micrometer. So one small division will be 10 micrometers as told you. So this is a calculation. I think this nonsense slide can be omitted. Now remove the stage micrometer and focus the wanted smear, in which we have to find out the size of the bacteria or polymorph or any other structures and measure the particular size with the help of ocular micrometer. Microscopic types. The optical microscope is the bright field, dark field, phase, fluorescent and confocal microscope. Electron microscopy several types. The first one is the scanning electron microscopy, this transition electron microscopy, the scanning transmission electron microscopy, and focus ion beam microscopy. Scanning probe microscopy can be divided into scanning tunneling microscopy, atomic force microscopy, near field scanning microscopy. So bright field microscope are simple. They contain a single magnification lens similar to the magnification glass. Leeuwenhoek used a simple microscope to observe microorganisms. So compound microscope has a series of lenses for magnification. Light passes through the specimen into the objective. Oil immersion lens increases the resolution. Have one or two ocular lenses. Total magnification is magnification of the objective into magnification of the ocular lens. Most of the condensers help in the direct light pass through the specimen. So the limitations of the bright field microscopy have a resolution power of approximately 0.2 micrometers, which allows most bacteria but not virus. So this is the bright field microscope or compound microscope, both are the same. Dark field microscopy. A special conductor is used to prevent the transmission of light directly illuminating the specimen. Only oblique scattered light reaches the specimen and passes through the lens system, which causes the specimen to be brightly illuminated against a. So the use to identify extremely thin bacteria like Treponema pallidum, Borrelia burgdorferi, Leptospira microfilariae, Cryptococcus. Advantages: the resolving power of the dark microscope is significantly improved compared to that of the bright field microscope. Disadvantages are light pass around rather than through the organism, and the detailed structure cannot be studied. Understood? So this is a picture which depicts the working principle of dark field microscope. So the differences: the bright field microscope is normally wide field illuminating method. In dark field, it is an opaque disc which is placed underneath the condenser lens. The background is bright and contrast is low. In dark field, the light is scattered. The dark microscopy has a dark background and the contrast is high. I think this makes it very clear. Phase contrast microscopes. So it was built in 1938. The principle is the parallel beams of light are passed through the objects of different densities. The wavelength of one beam moved out of phase relative to the other beam of the length. So through the annular rings in the condenser and the objective lens, the objects can be visually seen. Phase contrast microscopes. The difference in phase are amplified so that in phase light appears brighter than out of phase. This creates three-dimensional images of the organism or specimen, which permits more detailed analysis of the internal. So this depicts the working principle of the phase contrast microscope. So the advantages are the capacity to observe living cells, and such as the ability to examine cells in a natural state. Observing a living organism in its natural state or environmental condition can provide far more information than specimens that are killed, fixed or stained to view under a microscope. High contrast and low resolution images can be ideal for study and interpretation of thin specimens. Ability to combine with other means of observation such as fluorescence. Modern phase contrast microscope with CCD or CMOS computer devices can capture photo or video. Disadvantages: annually or ring limit the aperture to some extent with decreased resolution. This method of observation is not ideal for thick organisms or particles. Thick specimens can be distorted. Images may appear grey or green if white or green light is used, respectively, resulting in poor photomicrography. Shade-off and halo effect refer to the phase artifact. Shades of occurring with larger particles results in a steady reduction in the contrast moving from the center to the edges. Halo effect, which images are surrounded by bright areas which obscure detail along with the perimeter of the specimen. The microscope uses high pressure mercury halogen or xenon vapor that emits a shorter wavelength of light than the emitted by the traditional microscope. A series of filters are used to block the heat generated by the lamp, eliminate the infrared light, and select the appropriate wavelength for exciting the fluorochrome. The light emitted from the fluorochrome is then magnified through the traditional objective and ocular lenses. Organisms and specimens stained with fluorochromes appear brightly illuminated against a black background, although the colors vary depending upon the fluorochrome selected. The contrast between the organism and the background is great enough that the specimen can be screened rapidly under low magnification, and then the material is examined under high magnification once fluorescence is detected. So the dyes which are used are acridine orange, rhodamine oramine, and calcrophore. This is the fluorescence microscopy. So types of fluorescence microscope are transmitted and reflected light fluorescence. So transmitted light fluorescence is short wavelength light from fluorescent lamps such as mercury vapor or quartz halogen lamp passes through the primary excitation filter and then removes the unwanted colors of the light and passing only the red color. Transmission of this filter must match the emission peak of fluorochrome being used. The light is then brought to the specimen by a dark field. Special type of dichromatic mirror is used in reflected light fluorescence, which uses a interference filter. Light microscope through an excitation filter and directed into the dichromatic mirror located above the specimen. This mirror reflects the shorter wavelength excitation into a specimen and transmits a longer wavelength fluorescent light. Condenser is not used in reflected type fluorescence. Uses: examination of acridine orange stain in organisms like Microfilaria, Trichomonas vaginalis, treponines, Entamoeba histolytica, intracellular gonococci, meningococci can help in early detection of blood culture. Examining of rhodamine, oramine, phenol stains, sputum, and cerebrospinal fluid for acid fast basically can be done. Immunodiagnosis by direct and indirect fluorescent antibody test. Laser scanning confocal microscope. So uses fluorescent dye. The UV laser to illuminate fluorescent chemical in a single plane. Resolution increases between the emitted light and passes through the pinhole aperture. Computer constructs 3D images of the images. Important techniques for live cell and tissue imaging and studies of biochemical dynamics can be done using laser scanning confocal microscope. So the advantages are optical selection ability, 3D reconstruction, excellent resolution, specific wavelength of light can be used. The drawbacks are expensive, complex to operate, chemical labeling, and so this is how the images are depicted using a confocal microscope. Electron microscope. The energy source used is the electron microscope is a beam of electrons. Since the beam has an exceptionally short around 0.05 of the wavelength, it strikes most objects in its path and increases the resolution of microscope significantly. Viruses and some large molecules can be seen with the electron travels in vacuum to avoid contact with deflecting air molecules and magnets focus on the beam of objects to be viewed. An image is created with a monitor and viewed by a technologist. Limitations: cannot be used to observe organisms in wet living state. Transmission electron microscopy. Transmission electron microscopy uses lattice imaging resolution point less than 0.2 nanometers. In transmission electron microscopy utilizes the electrons that go through a very thin specimen. Scattered electrons that are strong interactions between electron matter are images diffracting pattern, that is X-ray spectrometer and electron energy loss spectrum can be used. No uniform distribution of electron contains all the structure and components. The excitation spot is 200 nanometers. By focusing the lens, a spread beam is used to quench the fluorochrome marker before they fluorescence. Very small effective fluorescence spot around 60 nanometers. Uses: to study morphological and chemical nature of the cell, cytoplasmic membrane, nuclear study of DNA integrity and irregularity. Molecular structure of flagella and fibria can be studied. Rapid diagnosis of viral diseases to identify genetics and bacteria which are difficult to culture or to stain. Example: Legionella pneumophila. So, how to care and maintain the microscope? So, the microscope should be cared and maintained like a girlfriend. Okay, the true one, not changing. Cleaning the objective. Dry objectives should be wiped using a soft cloth. Oil immersion should be cleaned using absorbent paper, and the oil should be removed with a dry piece of cloth. Moisten the cloth with saline and wipe the lens carefully. Wipe it again with the precaution. The oil should be carefully and completely wiped off the objective after use. The oil should not get on the 40x or the dry objective. Paraffin or mineral oil should not be used. Never touch the lens and never leave the slide on the microscope when not in use. When not in use, put the low power microscope on the focusing position. Thank you so much, friends. I think this lecture will be very useful to you. It took immense time and difficulty to prepare this. I refer nearly about 20 books, most of the books which MD microbiologist do. Hope this will help you. Thank you so much.